All right, so in this video lesson, what we're going to be talking about is what is called the empirical rule. And it turns out that this is actually a very useful tool that we have that we can use when we want to find what proportion or what percentage of the data falls within a certain number of standard deviations from the mean. And so what we're going to look at is basically three different scenarios. We're going to look at when you go out by one standard deviation in both directions, when you go out by two, and when you go out by three standard deviations. And so when you go out by one standard deviation, it turns out that about 68% of the data falls within one standard deviation of the mean. Now, when you go out by two standard deviations, you get up to 95% of your data. And finally, when you go to three standard deviations, you get 99.7% of the data, so almost 100%. And so because of that, and because of these numbers, the empirical rule is sometimes referred to as the 68, 95, 99.7 rule. So if you see that at all, that's what they are talking about. Now, when does it apply? Well, it only applies when you're looking at a normal distribution. And what we mean by normal distribution, as you can see below, is this symmetric bell curve. Now, the normal distribution is going to be centered at the mean, and then it's got that kind of nice shape to it where it's going out by 1, 2, and 3 standard deviations. Now, the other thing about the empirical rule is that it has to fall on a standard deviation. What I mean by that is that it's really only useful in going out by 1, 2, or 3 standard deviations. Anything in between, it's not going to be able to help you with. Now, there is some other things that we can do. In fact, that'll be what we'll talk about in the next section in order to still use the normal distribution to find percentages when they're not exactly on a standard deviation. All right, so here's what it looks like when you break it down. So you've got the 68% for one standard deviation, and notice that they're just using sigma for standard deviation, but you could have S sub x would work too. And then notice that you're then going out by 95% for 2, and that finally you go out 99.7% of your data for 3. And then basically everything after that, which it does continue on forever, but eventually you would get to 100% of your data. So let's break this up a little bit more. So if 68% is the first 2 standard deviations, then if you divide that by 2, that'll tell you that each piece of our normal curve is 34% when you go out by 1 standard deviation in either direction. Now, for the next one, we can't just take 95 and divide by 2. Because if you think about it, you've already used some of your data. But if we take 95 minus 68, that leaves us with 27% that's left over. And then if you take 27 divided by 2, is 13.5. That tells you that each of these pieces is going to end up being 13.5% of your data. Let's do the same thing for 99.7. So if we take 99.7, subtract away the 95 that we've already used, is 4.7. And then take 4.7 divided by 2 is going to be 2.35. So each of these pieces of our normal distribution is going to contain 2.35% of the data. For the last pieces, and they're really hard to see, but we're looking at kind of this piece right here and this piece right here. So everything that's more than 3 standard deviations away from the mean. If we take 100 minus the 99.7 that we've already used, we get 0.3, which then if we divide that by 2, we get 0.15. So each of those pieces is 0.15% of the data. So not very much, and it shouldn't be because it doesn't look like it's very much. Now, these percentages apply to any normal curve. And so that's why it's very useful, is that as long as you can draw a normal curve, you can use these percentages to find some different values. Let's take a look at an example of how this works. So according to the CDC, the heights of 12-year-old males are approximately normally distributed with a mean of 149 and a standard deviation of 9. We're going to sketch this distribution labeling the mean, and then the points that are 1, 2, and 3 standard deviations from the mean. All right, so first thing we need to do is we need to draw a normal distribution, and then we'll go ahead and label the mean, which is in the center of that distribution, which it told us the mean was 149 centimeters. All right, so let's go ahead and count up by standard deviations first. So if we go up by 1 standard deviation, remember a standard deviation is 9 centimeters. If you take 149 plus 9, you get 158. Okay, so let's go up by another standard deviation. So here's 2 standard deviations. Go up by another 9 is 167. And then finally, for 3 standard deviations, we're going to go ahead and add 9 one last time, and that gets us up to 176 centimeters. All right, so now let's go the other direction. So now we're going down by a standard deviation. So if we take 149 minus 9, we're at 140. Go down by another 9, 131, and then go down by one last standard deviation, and you end up at 122. All right, now those same percentages still apply to this normal distribution. So when it asks us about what percentage of 12-year-old boys will be over 158 centimeters tall. So over 158, I'm just going to shade that in here in red, would basically be these pieces of our normal distribution. Which when we look at that compared to our distribution above, that gives us 3 different values. We know that this value right here is 13.5, this is 2.35, and this is 0.15. So all we have to do, add those together, 13.5 plus 2.35 plus 0.15 ends up adding to be 16. So it looks like 16% of 12-year-old boys will be over 158 centimeters tall. All right, let's take a look at another example using this curve. So about what percentage of 12-year-old boys will be between 131 centimeters and 140. I'm gonna go ahead and shade that in blue here. And that's just one section of our graph. Remember that section, when we look above, corresponds to this 13.5 right here. And so this time we actually don't even have to add anything together. We can just say that 13.5% of 12-year-old boys will be between 131 and 140 centimeters. Okay, so let's do a little bit of problem solving. So suppose that we have a distribution of test scores that's approximately normal, and that we know that the middle 95% of scores are between 72 and 84. Then what is the mean and standard deviation of this distribution? Well, let's go and draw a picture. Let's kind of see what's going on here. So we've got our normal distribution, we've got our center, and then it says the middle 95. So remember, 95 is going out by 2 standard deviations in either direction. And it tells us that those values are 72 up to 84. So let's go ahead and find the mean first. If we want to find the center of our distribution, we can just find the average of those 2 numbers. So add them up, divide by 2. So that would be 156 divided by 2, which is 78. So it looks like the mean of our distribution is 78. And then to find our standard deviation, we just need to figure out kind of how much we're going up or down by. Let's just consider this interval from 72 to 78. And really all we have to do once again is kind of find the halfway point. So if we take 72 plus 78 and divide by 2, that ends up being 150 divided by 2, which is 75. Now that's not our standard deviation, but that tells us what this value is here. And now we should be able to see what the spacing is between each of the numbers. It looks like we are counting up by 3 each time, so our standard deviation would be 3. And we can check that. If we put in 3, 78 plus 3 is 81, plus 3 one more time is 84. So it does look like that's going to work for our standard deviation. Okay, so can we calculate the percentage of scores that are above 80? Okay, well, 80 would actually be a little bit to the left of 81. And we would want to know kind of what is this percentage? Now, we might be able to estimate it because we know at least what these values are. The hard part is this little piece that's just a little bit past 81. There really is no way for us to calculate that. So can you calculate the percentage of scores that are above 80? We're just going to say no, because the empirical rule does not apply. So the empirical rule only works if the value is actually on a standard deviation, which is what we were talking about at the start of this video. Now, again, in our next video, in our next section, we are going to have a way to calculate that, but we're not going to be able to use the empirical rule for it. All right, let's take a look at a couple more examples, and then I think that'll be it for us. So a survey of the teachers at Shawnee Mission North found that the mean morning commute times to work was 18 minutes. The standard deviation was 4 minutes, and it looks like the data was fairly symmetric. So we can assume that we can use a normal curve to sketch it. So we'll go ahead and do that now, sketching a normal curve going out by 1, 2, and 3 standard deviations, starting with our mean, which was 18. Let's count up by standard deviations first, and a standard deviation was 4 minutes, so add by 4 is 22, and then 26, and then 30, and then count down by 4s, so 14, 10, on down to 6. So for the first question, what percentage of teachers at Shawnee Mission North, that was a typo there, SMN, drive 14 minutes or more in their commute? So we're looking at kind of this piece right here, which we can go ahead and add up. This is 34, 34, 13.5, 2.35, and 0.15. But the easier way to do that is probably to do this. Half of our distribution has to add up to be 50%. So then all we'd have to do is, in addition to that half, we need to go another 34, and that adds up to be 84% of the data. Now, if you wanted to go ahead and add all those numbers up, you're more than welcome to. It's just sometimes a little bit quicker to think about if it's more than half of the data, go halfway and then count how much more you have to go to get to where you need to be. For part C, what percentage of teachers drive more than 26 minutes? So that would be these pieces right here. If we add those together, 2.35 plus 0.15, that adds up to be 2.5% of the data. All right, let's take a look at one last example, and then that'll be it for today. So 2,000 freshmen at State University took a biology test. The scores were distributed normally with a mean of 70 and a standard deviation of 5. We're going to label the mean and 3 standard deviations from the mean. And this time we were given our normal distribution, so we just have to draw in or write in our mean and our standard deviations. So our mean was 70, and then we're counting by 5s, which is kind of nice. So 75, 80, and 85, and then count down by 5, 65, 60, 55. All right. So for the first question, what percent of scores are between 65 and 75? So 65 is right here, 75 is right here. So we're looking at basically 1 standard deviation in either direction. That's actually part of the empirical rule itself. That's actually 68%. For the next question, what percent of scores are between 60 and 70? So here's 60. Here's 70, so we're looking at these values kind of right in here. Remember that this is 34, this is 13.5. So if we add those together, we'll get 47.5% of the scores were between 60 and 70. Next, we want to know what percent of scores are greater than 80. So we're looking at these pieces right here. Remember that's 2.35 and 0.15, and we've already added those together. We know that that is 2.5% of the data. For the next 2 questions, we want to know what interval captures 95% of all the students. Well, remember 95% is plus and minus 2 standard deviations from the mean. So if we go 2 standard deviations below the mean, we would have 60. If we go 2 standard deviations above the mean, that would be 80. So 60 to 80 would capture 95% of the students. For the next one, 99.7, that's just plus and minus 3 standard deviations. So go 1 more standard deviation in both directions. That would be 55 to 85. All right, that is it for this video. Like I said, in the next video, we'll talk about how you can actually use the normal distribution even when it's not part of the empirical rule. Until then, have a great rest of your day.